Good morning, good afternoon, everybody. We're going to give it 1 minute for people to roll on in, and then we can get started. I feel like we need like elevator music or something in the background. Well, all right, 9:01. Let's go ahead and get started. Good morning, good afternoon, everybody. My name is David with Tecton, and just first of all, I wanted to say thanks for joining today's webinar and talk. We have a pretty awesome session today, and we're excited to share with you what we're talking about. And so let me fire up this presentation really quick. The title of our session is Productionize AI ML Faster and Do It with Less Tech Debt. You might have come to this webinar because you're curious to see what it's all about. Maybe you're coming because you've heard of Tecton, or somebody in your company is already using Tecton and you're trying to get more familiar with it. Regardless of the reason of what brought you here, I think we can probably all kind of be in general agreement that there is a need of going faster. There's a need to productionize more models, to build more features, to get to market quicker. The demands are pretty high across our companies and businesses to do so. And I think ultimately, like, we all are very interested in what automation can bring to our engineering workflows for productionizing ML. And so within that, I'd like to take you through a quick agenda of what we got going on in today's talk. 4 different areas. The first is identification of what are those blockers. What are the big rocks that are kind of getting in the way of being able to advance models and get to market faster? Let's talk about what that looks like. Then let's talk about like rethinking some of the engineering workflows that are persisting in your day-to-day lives and kind of thinking about a new approach to how you can do some of those workflows. And then third, we'd love to share an introduction of Tecton and how we can ultimately help within your ML teams. And then obviously sprinkle in a bunch of awesome demos throughout the presentation end to end. And so, starting us off, like if we were to think about productionizing ML, where does all of the time go? And so if you look end to end across the development workflow, you can kind of see 2 large bodies of work. You can see a whole bunch of work on the data engineering side, and you can see a whole bunch of work on the model engineering side. On the data engineering side, this is all about turning raw data into the right input signals that models need for training and inference. On the model engineering side, it's obviously all about training and deploying models into production. Where we're going to focus today's talk on is really about the data engineering side and having a close look and examination of all the different levers, all the different choke points, all the different ways to think about data engineering in a holistic way, that what we see and what we hear from our customers is the biggest drain on resources. A great example of this would be DoorDash. In 2022, not that long ago, DoorDash had written a post that said 70% of their ML team's time is spent on feature and data engineering. And so this is obviously a pretty massive consumption of time that could be better spent on the models, on the applications, on discovering new use cases, building more apps, and so forth. And so the ultimate opportunity here is to see, how do we think about the 70% of time in a new way that could conceivably allow the productionization of models to be faster than ever before. And so I think in order to understand this bottleneck, you kind of have to take a step back and think, okay, where is the data engineering? What's involved? What matters and why? And I think it requires having an appreciation for features. And we all know when it comes to machine learning that garbage in equals garbage out. And so you have to have the right data, the right features, the right input signals that could power these models for the best, most accurate predictions, drive better model performance, even drive better compute efficiency of the models themselves at inference time. And that requires looking at the end-to-end data workflow, everything from how you define and experiment new features to the productionization of those features, and ultimately the serving of those features for training and inference. And, let's say hypothetically, like you and I are building a new recommender system. Let's say we're building the next food delivery service, and we want to build a Rexis that allows the application to serve the best recommendations for which restaurants we should be having customers choose from. Right. And so if we're going to build this recommender system, we're going to get together as a group. We're going to have data scientists, MLEs, product owners. We're all going to get together. We're going to think about, what are some relevant signals that are necessary to build an accurate model? And we'll probably think of some batch-based features, like what's the age of people that are using the app? How often are they visiting the application or the restaurants? What are their favorite preferences for cuisines? We might also have streaming-based features, things that are more, closer to the kind of real-time nature. And so we'll be looking at features like the average ratings, number of likes that's happened in the last hour, last day, what's currently trending and popular, what are different promotions that are currently being run by different restaurants. And then we might even be looking at real-time features that are looking at like current in-transaction type input. So what's the current load like for a particular restaurant? What's the GPS location for where we are and where drivers are? What's the current traffic look like? And how's that going to be a factor in terms of how long it will take for a delivery to be completed? And so we'll look at these different types of features across these different buckets, and then we'll start recognizing some kind of challenges from a data engineering standpoint. We'll be thinking about what's the location of where this data lives. Maybe it lives in Snowflake, maybe it lives in S3, or for the streaming data, maybe it's in Kafka, maybe it's coming from a third-party source, or for the in-app, in-transaction data, this is actually what's happening right now, like the GPS location and other inputs from third-party sources. Then we'll think about, okay, well, if we have data in different places, what processing engines do we need in order to compute the right necessary features that we need? Maybe we're using dbt. Maybe some data sources need Spark. Maybe we're thinking about streaming data and we need Flink or Spark structured streaming. Maybe we need to build custom scripts to support real-time computed features. And then we're going to be thinking about the update frequency. Every feature needs a different type of update frequency depending on the patterns that are necessary for those algorithms. Maybe it's monthly, maybe it's weekly, maybe it's in minutes or seconds, or maybe it's instantly based on real-time computed features for real-time features. And then we got to think about, okay, well, in order to get all of that to happen, we also have to orchestrate all of the data pipelines that are necessary in order to support all of these features and the materialization for both backfill and forward fill, carrying it all the way out into inference. And so now you're building a bunch of Airflow jobs or a bunch of cron jobs, and that is obviously adding a lot of work and complexity. And then ultimately, there's a bunch of people, right? You have a lot of different systems that you're needing to integrate and work with, a lot of custom code that's involved. And so within all of that aspect, there's a lot of work here. And so ultimately, you kind of think about this view. We could also think about the development work for the data engineering aspect of ML kind of more from an experience standpoint. And so what do I mean by that? Well, our customers have shared with us that there are 4 predominant choke points that are serving as like the major bottlenecks from a data standpoint when productionizing ML. The first being the experimentation phase. We hear from people and ML teams that it's difficult to experiment with new data, to define new features across streaming, batch, real-time data in a consistent way, also generate point-in-time training data sets, and having to do all the complex joins that are required in order to complete those training data sets. Ultimately, the experimentation phase comes down to a lot of different processing tools to work with, a lot of different infrastructure that you have to manage, and ultimately a lot of data engineering that's required to write all the code out to do the experimentation of those features. Well, that's only step 1, right? Step 2 then becomes a productionization challenge. So once you have your features defined, you want to be able to backfill that data, you want to be able to forward fill and materialize that data source. Well, in order to do that, you're going to have to rewrite those features, and you have to build up those data pipelines, and you have to do so in a way that's quick, reliable, and accurate. And there's a couple different implications that happen here on the productionization side. Well, you're going to have to build a lot of different discrete data pipelines to support both your offline training as well as your online inference. You're having to ensure data consistency, so you don't have any training serving skew that's occurring across your online offline store. You're having to ensure process dependencies are completed in order. You have to build automatic retries and error handling to ensure those pipelines are hardened for reliability. And then you also have to optimally design your data model so that you're able to store and persist those pre-computed features in a way that's pretty resource and performance efficient. And assuming you can get past all that stage, then it's about governance, right? As you increase the number of features that you're going to be working with, then it becomes a governance challenge. You have pipeline sprawl, you have multiple pipelines, you need to have the right visibility into all the different features that you've created, and you do that in a way that's very scalable. And then last but not least is obviously on the serving side. So serving both for training, serving as well for inference and predictions. How do you design and develop and maintain the right system that allows for the right throughput, the data freshness, the low latency, the high availability nature that's needed on that serving infrastructure? And so when you look at all of these things in totality, there's a lot of systems that are required. There's a lot of systems that have to be integrated, a lot of systems that you have to work with. You have to do a lot of manual coding in order to develop the workflows that are necessary to support all four of these stages. And ultimately, that means that it becomes much challenging for organizations to scale their feature engineering, their feature development, their feature productionization, what have you. And so take this into a more real kind of context. Let's say, for example, that you are in a development team and line of business owner comes in, or a product manager comes in and asks the question like, hey, I came up with a new feature around number of failed logins. Why is it taking so long? Why can't we just add the number of failed logins over the last 2 weeks to the fraud model? Like, that should be simple enough, conceivably, right? But we all know that under the covers, it's more difficult than what meets the surface or meets the eye, because the login data is probably living in Kafka. Well, this Kafka topic itself only has 1 week's worth of data. So you have, one or two approaches. You could go log and wait for the Kafka pipeline to have enough historical data so that you have enough data for your training. Or alternatively, you can go to your data warehouse, which would have and persist all of the existing failed login data that already lives out there. But then you're going to have to build your complex sliding time window aggregations. You're going to have to build and maintain the data pipelines. You're going to have to build out the point in time correct join that's necessary in order to build the training data set, right? Because now you have your hundreds of existing features that you've already defined, and you're adding a new feature into that mix. And now you're going to have to retrain that model. So now you're going to have to do some crazy join operation that has hundreds of different joins and now ensure the point in time correctness. And that's just really on the training side. You obviously look forward, and we kind of go through it on the slide, and there's a whole bunch of workflow work that's involved on the prediction side, and being able to have the right data that's necessary to support inference, having to build a Lambda architecture because you need 2 weeks worth of data, right? In your online store, well, you got 1 week of data in Kafka, and then you got 1 week data in your Snowflake data warehouse. Now you got to create a Lambda function in order to support, multiple different locations of data into one data set, and then be able to have that in a consistent way that could be served for predictions as well as for training. And so ultimately, all of this ends up being like a lot of work, right? And that's why when we talk to our customers, before when they look at their development workflow and they think about data engineering, they realize that it's taking weeks to months to produce a new feature. And something that always kind of baffled me and surprised me is that in a world where iteration is seen as valuable, where you want to try new features, you want to have an experimentation, you want to be agile in that approach of trying new features, testing against the model, and iterating quickly, weeks to months is very slow. And that's why we hear this a lot from companies is, what if we could solve the data engineering bottleneck? What if we can reduce the amount of time that's required to turn raw data into engineered features and then serve that into training and inference? And so what does ideal look like, right? What is that ideal feature workflow that could resonate with you and your use case teams and your platform teams across your organizations? Well, we kind of see it from a new perspective, a new paradigm, effectively, that's built on abstraction. That in an ideal world, it would be fantastic if your data scientists or machine learning engineers could simply define a feature in Python, irrespective of its data source. This is unified processing at its finest. So streaming, batch, real-time data, all done in Python. And then when you're time and ready to commit that feature into production and materialize them, the pipelines get built automatically. Like, could you imagine that kind of environment where your pipelines are actually built on your behalf? The materialization is done automatically. The orchestration is done automatically. The resources are managed. They're spun up, they're spun down. Your data modeling is done automatically. The consistency of sending data across your offline store and your online store is done automatically. And then when it comes to serving infrastructure, you have an API that you simply access to retrieve the right features at the right time, as well as compute like real-time features on the fly as well. And so from our perspective, that's where our customers, that's where teams that we talk to, that's the ideal state of automation when it comes to productionization of ML, is how do we get rid and abstract all of the underlying data engineering that's involved to get new features into production, which ultimately impacts their end-to-end development workflow for their models. And so that's ultimately what Tecton's about, right? And so Tecton is a unified feature platform. Our mission in life is to make it very easy for ML teams to turn raw data into engineered features, to be able to manage those features at scale, and to be able to serve those features for any training or inference production SLA that's required of them. When you think about Tecton, there's 4 key components that make up our platform. The first is a declarative framework, and we'll talk more about each one in a moment. But the declarative framework is, how do we make it very easy for you guys to be able to define new features and have those pipelines built automatically in the background? Specialized feature engines. Specialized feature engines are pre-built processing modules designed for very complex features that we've hardened in an end-to-end pipeline that makes it very easy and repeatable to be able to leverage. And we'll talk more about that in a second. We have an enterprise feature store that facilitates the ease of managing, governing, lifecycling your features. And then we have a unified serving system that's process optimized that allows for the ease of being able to support any SLA across latency, throughput, availability, and so forth. And so kind of diving into each one, let's talk about first, like, what is a declarative framework? Like, how can we think about this new way of doing feature engineering and productionizing features? Well, our declarative framework effectively is an abstraction. It's an abstraction that makes it very easy in a unified way to define any feature, irrespective of its data source. This could be streaming data, batch data, real-time data. Define that feature really easily and then productionize that feature in the background without you having to build any data pipelines. And so the way to think about the framework, there's like 3 core components. The first is defining your features. So in the comfort of any notebook of choice, you simply utilize our SDK, and our SDK is a Python-based SDK that allows you to simply define a feature by declaring your goal state. What does that mean? Declaring your goal state. Well, what is the end state of that feature that you're trying to develop? What's the data source? What is the feature transformation logic that you want? What is the update frequency? Do you want that feature to be persisted in both an online and offline store? Really, really simple declarative way in Python to declare and define what that feature needs to be. So you can have your data sitting in Snowflake. You can have your data sitting in Kafka. It doesn't matter, because you have one unified language that makes it very easy for you to define whatever that feature needs to be for your application. And that makes things very easy. So you kind of imagine, if you roll back the clock, that was always the goal of what Apache Beam was, unified processing. And that's effectively what we've built when it comes to defining your feature, is how do you define those features in a unified way, irrespective of the data source. The next stage is really about training your data, right? So when you leverage our SDK, building training data sets is like radically simpler. And you're going to see a demo in a moment, but you're not having to do a bunch of join operations. You're not having to do point in time joins to create the consistency that you need to align with the events. You're not having to worry about time-based alignment. You're not having to worry about partitioning. You're not having to build any complex, data engineering, SQL logic or code, because training becomes so easy because we build the point in time training data sets in the background through a very simple code statement that you see here on the right. And then when you're ready to say, hey, I want to productionize this feature and I want to commit it into the feature store, all you have to do is execute a simple apply command. And then in the background, Tecton builds data pipelines. We automate and orchestrate those pipelines. We run and manage the underlying infrastructure, and then we carry that all the way out through so that you're able to apply those features and have an end-to-end pipeline executed and made available through your feature store. And ultimately, what you end up having, as you can see here in this DAG and through this visual, is a very, very clean way of having quick, reliable, accurate feature pipelines for all of your features. And you don't have to worry about the consistency across your online offline store. You don't have to worry about managing out of memory issues in Flink or Spark or dealing with resource management of your underlying infrastructure. Why? Because Tecton's taking care of it, right? You're not having to harden for reliability. You're not having to build in error handling. All of the work that's involved with building your feature pipelines ultimately evaporates. And so you kind of think about, well, what does your development workflow look like today? And what does your Jira board look like? And this is the kind of stuff that we see from our customers is where they're spending their time. They're spending their time building the systems in order to orchestrate this. They're spending the time fixing issues, dealing with serving latency issues. They're dealing with training serving skew. They're dealing with different rogue issues that are happening across their environment. And ultimately, this is a magic wand that allows them to make it much easier for them to just simply declare the feature they want and get it out into production. And so the way to think about this that I kind of like is compare it to what Terraform has done for infrastructure, right? Cloud infrastructure always existed before Terraform, but they made it so much easier to provision applications through infrastructure as code, through a declarative means to declare what infrastructure you needed to support different apps. We're effectively doing the same for features where you can declare what features that you want. And then in the background, we can build the pipelines and orchestrate the infrastructure for you so that you simply have an API at the other end to access those features that were already pre-computed for you. Or if you want, you can obviously do real-time features as well, which is a strength of Tecton too. And so the second aspect of Tecton is really about our specialized feature engines. We can support any variety of feature transformations that you have, but there are a handful of very hard, complex, but common patterns that we see from customers that need a little bit more like engineering that's involved in order to execute these features. One, for example, is a time window aggregation. Say, for example, going back to that login example, that you need to aggregate the number of logins that accumulate over the last 5 minutes, but update that every minute, right? Well, if you're going to be building out a feature like that, you obviously it's more challenging and complex because you're now dealing with stream processing. You're having to work with Apache Flink. You're trying to deal with the resource management constraints that exist in that tool. Or maybe you're saying, forget that. I'm just going to take every raw event. I'm going to persist that into my key value online store, and I'm going to query the right feature at inference time. But then you're going to have latency at the serving side. So what we've done here in this first dimension of a time window aggregation is we've built a specialized feature engine that we call an aggregation engine. An aggregation engine makes it very simple because we've architected the data model in such a way that makes it very easy where we can support, very efficient performance processing to complete time window aggregations and do it in a repeated way. So for example, let's say you need a 5-minute time window aggregation. Well, we call these tiles. We'll create a tile for every 5 minutes and that go out into the future that generate that generates the data point that you need for every 5 minutes. But what if you need a feature that actually looks back every 10 minutes? Are you going to go back to the source and now recompute a whole new feature based on a 10-minute sliding window? Well, in a historical context, yes, if you use traditional tools, you would have to do that. But in Tecton, you wouldn't have to because you can simply aggregate your 5-minute windows that you've created to create 10-minute windows and do that with low latency at serving time. And so this is an example of a specialized feature engine. Another specialized feature engine that we've created is our embeddings engine that we've recently released into private preview not too long ago. And the embeddings engine allows it very easily through our service to take raw unstructured data, run it into an embeddings model, and then output the right vector embeddings that we can create for you. So again, think about all of the work involved with having to build out the data pipelines and the data engineering to compute an embedding. Well, that's all handled under the covers now by Tecton simply as an embedding service. And so within that, I'd love to actually hand the mic over to my colleague, Sergio, who will take you through a demo of the whole declarative framework.
All right, let me find the right screen and get this going. Okay, well, hi, I'm Sergio Ferragut. I'm a developer advocate here at the Tecton. And what I'm going to walk you through here is essentially a notebook. So this is the environment in which we expect data scientists to work, and where most data scientists work. And we're going to focus on the feature engineering side of what a data scientist might do as they build out a new model, right? So the first cell that we see here is a simple log, the imports, the initialization, with one important aspect. We're logging into the Tecton platform and selecting an account. In this case, we're in the community account where we do demos, and we're also selecting. Let me just point out that we're selecting the engine that we're using. So there's two different distinct options with Tecton. You can use what's called the Rift engine, which is a lightweight engine that allows us to run things more speedily in many cases, because we don't have to start up anything that takes time to start. But if you have larger data sets, much larger data sets, you can also use Spark as an engine and drive calculations through Spark. Anyway, but this example is using Rift. Once we've logged on, I'm just going to walk through what a data scientist might do as they build out a fraud detection model. So the examples are related to a fraud detection model. The first thing a data scientist will do is examine some data, right? So in this case, we have some transactions data that's in an S3 bucket, and there's nothing new here, right? This is just pandas, somebody reading a Parquet file and examining data. And this is just to describe the normal flow of a data engineer. Of a data scientist would be maybe something like this to start with. Now, with Tecton, we do ask that the data scientists, as they start defining features, that they describe them in the terms of our declarative framework, right? And when we talk about this declarative framework, it's actually a specific set of objects and how and how to declare data sources that can be streaming, batch, or request time data sources, the entities, the business entities that they're going to be defining features for. And then the feature views that actually define how the data, how the data source is transformed, whether in stream fashion, in a batch fashion, or on demand as needed at request time. So the feature views define the transformations of the raw data that can then be served as features. And finally, the feature services, which give us the ability to take subsets of feature views to create feature vectors that are needed for both serving and training, where the objective of the feature service is to provide low latency serving to the inference side of the equation. And also this concept of time traveling training data, where it's taking care of all those point in time joins across different feature views and across different granularities of time and different aggregations, and just figuring it all out for you so that you get point in time consistent data and avoid that training serving skew. So that's the declarative framework at a high level. What I'm going to walk through is a streaming example. So how to create a streaming source, a streaming feature view, and then how to use that to obtain training data, and then how to use that live. So the first part is creating a streaming source. It's really this simple, right? From a data scientist perspective, they just need to give it a name, need to figure out where the stream source is, right? In this case, we're using what's called a push config. This can also be a Kafka config or a Kinesis config. A push config allows you to push data directly. So it creates an endpoint where people can submit data through REST APIs or directly through Python, as you'll see here. And then also define a batch config. Now, it's interesting to think about a streaming source that requires a batch configuration, but this is actually something that is a best practice in dealing with streams. So it's not just about processing the event as they come, but it's also about solving the out of sequence events that may occur in a stream situation where you may have some events that occurred at a particular point in time, but for some reason are delayed to getting into the pipeline, into the Kafka topic, or submitted to the push config. And that event actually refers to something in the past. So as the aggregations occur live on the streaming side of it, they may miss some of those elements that occur out of order. The batch config allows you to solve two problems. It allows you to solve the history. So where's the history of this message topic or the stream, so that we can do backfill operations and create the history of the feature set. And also to do the incremental updates of those as we record features into the offline store, do the incremental updates of those that take care of adjusting those incorrect in time events that are out of sequence events that occur in streaming situations. So it's from the get-go, it's getting you into the mindset of how do I deal with these out of sequence events, and getting you to configure it the right way. So back to the basics, we're defining a streaming source here. We're defining how the stream is pushing the data with the stream config, and we're defining where to get history for backfill and where to get the incremental data as this process is deployed and those time fixes are necessary. So that's it for the streaming source. The schema defines which fields out of the data that's coming in we are actually going to be using, and that defines the stream source. Now you can test the source. That's just probably something also that the data scientist will want to do. And so it's really just as simple as taking the object we just defined, this transaction stream that we defined up here, and get a data frame from it with a time frame. In this case, the data scientist maybe not ready to do the training, so it just needs to see a test of the data, maybe test how they're going to transform those events into features. So this gives them the opportunity to examine that data source directly. Then the next step is to create the feature view. This is where we're transforming the data. Every feature view needs to have associated entities. This is how we associate a set of features to a user, to a location, to a merchant, whatever the business entity of interest is. And in this example, we declare it as a stream feature view. This means that it will be processing live from a streaming source. We declare what source it's going to use, which entity or combination of entities it's creating features for, and the mode of execution. In the streaming case, well, depending on if you're on Spark, you could do Spark structured streaming with Spark SQL. If you're on Rift, you can do just pandas directly, or even just basic Python for the speediest calculations and the least resource intensive calculations. Aggregations are defined this simply as a list of what the aggregate function is, what column it's aggregating on, and the time windows defined for them. And you can define any list you want of these aggregations and different time frames. And that's all you need to do in order to build out these aggregations. The function itself, right? This transformation function that defines how the raw data is being transformed is really just Python, and you could do anything you want inside this function, right? In this case, we're doing something very simple. We're just taking the source, which is the transaction stream, the same source that we read from here, and where the columns that we're going to be reading are going to look like the data frame that we got up here. So we can take that data and transform it in this function in any way we want, a row at a time, or in the case of Spark SQL or Snowflake SQL, you could drive some aggregations down to the source, right? So this defines how the transformation, how the raw data is going to be transformed, and creates an output that is going to go into the aggregation engine that David described and generate all of these aggregations with that efficient aggregation engine. And this is that is the full definition of the feature view, right? With this, we've defined the source, we've defined what entity we're creating features for, we define the features that we're creating, and we can take a look at the data at that point. You can read that directly, and this works in two different ways. When you're running it as a data scientist, you're in the SDK, so you're interacting with Tecton, and as you run these things, it will produce the data and actually go and build out the pipeline in your computer. If you're running on your laptop, it's going to be running on your laptop. If you're running on a bigger node, it's going to be running there. If you're running on a Databricks notebook, it's going to be running in your Databricks environment. And you can access the data directly. The whole point is the data scientist has this ability to do their work like they normally would. All we're asking is that they use this declarative framework to do the feature engineering work such that it's directly applicable to a production environment. The next element is the feature service. This is what exposes a set of features from one or more feature views. And it's really as simple as this. We're giving it a name, right? In this case, the fraud detection feature service streaming that reads off of this streaming feature view. It could have this streaming feature view and an associated batch view and an associated on-demand view, and pick features from all of those, and it will automatically take care of doing the appropriate joins in the case of building training data, or doing the serving from the appropriate online store for each of those feature sets. So it builds out the feature vector that you need with low latency in the serving case, and it builds out the training data sets as needed for the same set of features, therefore avoiding completely this training serving skew, because we are defining how to calculate the feature in one way, right? And that single way of calculating it is used both for the offline and the online features. In this next cell, we're using that particular feature service to get a training data set. So in this case, we're reading transactions. So this is normal work that the data scientist would do, reading transactions to get things like the transaction ID and the user ID, and the time of the transaction, maybe the amount of the transaction, and then getting labels for the training itself. In this case, the labels would have fraud, whether that transaction was after the fact labeled as fraud or not, because we're trying to create a model that predicts fraud. So that creates the training event that we're going to train on, and then we can use the feature service directly here to get features for those events. Right. So what that'll do is it'll look for those entity IDs. So in this case, we have the user, and the user ID is what it's keying on, and it'll automatically key on the entities that are involved in the feature views, find the right set of features that are associated to the right time of the event, so the timestamp that we're on the transaction, and build out the feature set based on the feature view definition. So in this example, you can see the output. We have the data from the transaction, the user ID, the timestamp, the amount. We have the label that we associated to the event, and then we have all the features that we calculated: the 30-day continuous aggregation of transactions, the 1-minute continuous aggregation, and the 1-hour continuous aggregation that we defined up there. Once you've defined all of this, you do what we call a Tecton apply. Tecton apply is where we take these this object definitions, the data source, the feature views, the entities, and the feature services, and we're essentially putting them in. It's a copy paste operation that's handed off to the data engineer. Right. This is usually integrated with GitHub and with CI/CD pipelines. So the data scientists may be working on one workspace where they do their experimentation, and when they're ready to produce a new set of features for the data engineer to optimize, they put them based on those objects. The data source, this is just a copy of the data source that we define, a copy of the entity, a copy of the feature views, and finally a copy of the feature service that they need. They publish this into a GitHub repo, and there we have CI/CD pipelines where there may be a review by a data engineer, and then a publishing of that into production. So when we do that publish to production, let me show you what the output looks like here. Is we just do a Tecton apply of that set of object definitions, right? The data sources, the feature views, and the feature services. And what Tecton will do is automatically analyze the current workspace. So if it's the production environment that we're applying to, it figures out what the changes are, what feature views have changed, what data sources have changed. So it figures out what changes it needs to make to the pipelines. And then it goes and it deploys the pipeline. So it deploys the scheduling of backfill jobs, if backfill needs to reoccur, if there has been a big change in a feature view, for example, or if there's a new feature view. And it schedules the incremental processing, both of the stream and the batch forward fill that occurs also on a batch basis, and so forth. Right? It does all of the scheduling, all of the provisioning for you, and that's it. That's it from a data scientist and data engineer's perspective. I'm going to do a quick check on time, and I'll check on Q&A here, see if I have to answer any questions. And give it back to David for a second before I continue demoing.
That was fantastic. Thank you, Sergio. Let me fire up the rest of the presentation. So we obviously had a great walkthrough in terms of the feature engineering and feature productionization process with Tecton. The next step of it is, well, what about management? What about governance? Because when we're dealing with a lot of features, now we have to think about resource management, we have to think about life cycling, we have to think about security and governance and all that good stuff. And that's where our feature store comes in. I think historically people have thought of Tecton as a feature store, but it's really more of an end-to-end feature platform. A feature store itself is really about the storing and the management of pre-computed features and ensuring the consistency across the online-offline store. And we do that really well, right? And so within our enterprise feature store, we make it very easy to see the life cycle of all your features. We make it very simple to have a single pane of glass. You can see the metadata associated with every feature. You could access features, you could search features, you can discover existing features, and you can promote the reusability of features across different use cases and across different teams inside your organization. The reason why we call our feature store an enterprise feature store is that it also has all of the access controls, the RBAC, the encryption that's necessary in order to support the needs of enterprises as you think about managing and privacy of all of those data sets that are ultimately being stored within Tecton. Last but not least is really our unified serving system. So when we think about the serving infrastructure that's required, one thing that was new to me was that as I learned more about Tecton is that the performance of features for both the retrieval side on inference as well as for training is more than just the underlying data store that your persisting stores. It's more than just S3. It's more than just your key value store. In order to ensure the right throughput and the right low latency that's necessary, for example, on the training side, we've built serving infrastructure, auto-scaled serving infrastructure that can handle those large data sets that support the quick retrieval for training. On the training side as well, we build the point-in-time accurate training data sets that Sergio had referred to. And so you're not having to join hundreds or thousands of different discrete tables where every table consists of a different feature. Join all of those, align the timestamps to ensure the point-in-time accuracy against the training events. All of that happens in the background through our serving system. On the inference side as well, we've built a very robust real-time serving system that supports both real-time compute for those features that are unable to be pre-computed. Perhaps the data is just generated in the moment in a transaction, and therefore you can't compute them in advance. And so we can do that swimmingly well. And we also can support the high throughput, low latency requirements as well, exceeding well over 100,000 requests per second and executing those that high throughput requests for inference in under 5 milliseconds. And so you're seeing a very capable serving system under the hood that's built because of what we're able to orchestrate through Tecton's declarative framework. And so that kind of begs the question of, well, is Tecton, is Tecton a development experience? Is Tecton data infrastructure? Is it a little bit of both? And so I think this slide hopefully will make it very easy for you to see is that we're ultimately trying to drive a development experience for our customers. And so the declarative framework makes it very easy to interact with Tecton to declare those features that you need, and then be able to retrieve those features through our SDK and API. But when it comes to computing, we provide flexibility and choice for our customers. So when it comes on the compute side, you can leverage your existing EMR, your existing Databricks Spark environment, your existing Snowflake, and we can push down compute orchestrated through our declarative framework. We can push down compute into the existing systems that you already have, and we run those systems optimally. We spin up the clusters optimally in a way that you're going to have a very efficient processing and computation that's required to create those features. But on the compute side, we also have a managed service called Rift, which we introduced just at the end of last year. That is a fully managed computation or compute system that allows for batch, real-time, as well as streaming features to get computed through our managed service. And that's using Rift, and that's completely Python-based. And so we have a lot of flexibility and choice on the compute. On the storage side, as well, flexibility and choice, right? S3 for your offline data. You can actually store your offline data in your own environment as well. But on the online side, you can use Redis, you can use DynamoDB. And so we provide a lot of choices there, as well as you can use your VectorDB database when it comes to the embedding service that we provide. And so ultimately, this is about ease of integration and driving a development experience for our customers. And so within that, I'd like to hand it back over to Sergio to take us through a demo of the Tecton UI. Hey, Sergio, you are on mute.
Well, and I was answering questions on the other end. So let me share my screen again. Here we go. Okay, so let me let the screen refresh. So we ended up in the Tecton apply, and that means that we're sending a bunch of stuff into the platform, and the platform is going to materialize these things. So this is a view of a workspace. So if I start from the top here, you can select multiple workspaces. You see, well, all of these are live. They don't necessarily need to be live. This is the prod, where we have a set of multiple feature views. We have examples of batch feature views, streaming feature views, and even on-demand feature views, which are the three timings that we talk about where features need to come in different with different event time to calculation latencies, right? The batch latencies are measured probably to a minimum of an hour or so for mini batches, where streaming is an async but near real time kind of calculation, last minute aggregations, that kind of thing. And the on-demand features are the ones that need to be at the time of the request, right? When the inference is going to occur, we may receive some data with the inference request that goes through some other transformation and some comparison to other features and so forth to build the final features before doing the inference. So you can see it all here in the deployment. So it gives you a full view of how the online and offline feature stores are being created and how the feature services are being calculated with full lineage of where data is coming from. It also gives you a great environment for reusability and discoverability. There was a question there about, how do you avoid feature sprawl, right? Well, one way to avoid feature sprawl is to centralize all of your feature generation, and that's what the platform provides. And so you can go and investigate features directly here. So a data scientist is embarking on a new project in a mature feature environment where there have already been many features created, both streaming features, batch features, and there's a richness of feature availability already on the platform. They might come here and see, okay, what information do we have on by entity? So they can see, okay, let's see what we have on users, and they can filter it quickly and see what features are already being calculated, look at the details of each of these feature sets, what aggregations they're building, on what quantities, and therefore be able to reuse work that's already been done. And that's a key element of a good feature platform, right? Where data scientists don't need to reinvent the wheel from the beginning, right? They can go in and from this catalog do a few selections, and then I'll show you a little more on how that would be, from a notebook perspective, because they're not always creating new things like we just did, right? They could also, let me move this down. They could also just be reading. Where am I? I'm in the wrong one. They could be reading things that are already there. So Tecton applies have already occurred. There's a bunch of feature sets, feature views already in place. So they can access the platform, access a workspace to get the information from a particular workspace, access data sources directly, access the feature views directly, and then just use those directly in their code to follow up on an example. I'm going to do a time check here to see how much more time. Okay, we have some time, so I can walk through a little bit more of this example, where just to complete the idea. So the user, the data scientist, has gone to the UI, has found the features that they wanted. They come here, just access the feature views directly, or even the feature service directly, to test it out, right? They can, because the data source was configured with a push config, they could actually push data into it directly with the ingest API. So you can see here that we're using the data source that we got, the transaction stream that we got from the platform. We're using it to ingest a single object. This could be a single object, or it could be an array of objects, so you could batch them. And that is essentially pushing data into the data source and through whatever pipelines are defined on that data source. So when we do that, let me go ahead and run a few here. Run a few this morning. This is for each one. It's actually going and establishing a new connection and submitting the request, receiving the response. In a production scenario, you wouldn't necessarily do that. You might have, a connection pool where you're pushing events if you're using the push API, or you've connected it directly to Kafka. So I say all that to justify the 15 seconds that just went through for those three events. And then you can use the feature service directly to see them, right? So we can look at the feature service. We've defined a particular user. So I defined up here a particular user I was working with. So I'm sending transactions for a new user, and I can see immediately down here the features that we're calculating on that feature view, right? Where we're distinguishing between the hour and the 30 day. The hour and the 1 minute are including the transactions I just added, where the 30 days also including the ones I did this morning. So you see the differences there. And if we wait around here for a minute, which I don't know that we want to do, you could also see the difference in the minute and hour, like I done in the experiment earlier today. Let's see if we get the difference. See if I talk long enough. I did talk long enough, so there is a difference now between those two. So you see how these continuous features are working, and the data scientist can use them directly off of the feature platform. With that, I mean, I could navigate a little bit more. You can see all the entities that have been defined. Transformations are common transformations that can be reused from features to from feature views to feature views. These are things like maybe we're converting, Fahrenheit to Celsius, or common calculations, maybe changing the currency to the user's currency, or doing something with a little more intelligence. That's a common operation that data engineers don't want to be recoded multiple times, so they create transformations that are meant to be reused, and so forth. The features which we've talked about, the services, where we see all of the feature services that are already deployed and live in the platform for the workspace, where we can control permissions. I won't get into all of the security side of it at this point because we don't have that much time. But anyway, and back to the global view where you can see everything that's been deployed. So with that, I'll stop the demo and send it back to David.
Cool. Thanks so much, Sergio. And I'm going to bring us home now with like 2 or 3 remaining slides. So we've talked a lot today. We've talked about the declarative framework and how it makes things easier through a new development experience to experiment and productionize your features. We talked about the governance and the management of those features using our UI. We talked about the serving infrastructure that we provide under the hood that allows for the very fast retrieval of those features for training and inference. Why? What does it all mean? What ultimately are customers and companies getting out of it? There was one question question also in the chat around any kind of large enterprises that are using our platform. And what we're sharing here are a couple of customers and some quick use case examples to show what is the value been and who's using Tecton, first of all, and what's the value been of Tecton for their businesses. For confidentiality reasons, we can't reveal all of our customers' names because of the privacy that they've asked for, which we acknowledge and appreciate. But three core outcomes that I would talk about. The first is about productionization of doing more, going faster, doing more with less. And we heard recently, I heard a story about how one of our customers had actually shared with us that without Tecton, they would have a team of 20 data engineers doing the work that they no longer have to do because all of the automation that's happening because of our platform. That's pretty remarkable. A Fortune 150 insurance company that you see here was able to shorten their model build time, not their feature build time, but their model build time was able to reduce from 16 weeks down to 2 weeks because they're able to streamline feature development and increase the reusability of existing defined and productionized features. That's pretty cool. The second major outcome that we've seen for our customers is the enablement of building better and more accurate models. By having more access to more data, having the ability to iterate quickly and experiment with new features, and the ability to eliminate the training serving skew, Atlassian, as an example, was able to increase their prediction accuracy to 99.9%, which has been pretty game-changing within their predictive models. And the third dimension of why or how customers are getting value out of the platform is really about an overall lower cost of ownership. Clearly there's an efficiency in terms of productivity and the ability for really talented MLEs and data scientists to work on value add activities. But it's also about the core cost of infrastructure, right? Managing all of these different bespoke systems is complex work. Often over provisioning occurs. And when you think about what we do under the covers, we're actually managing this infrastructure on your customers, on your behalf in a very efficient, elegant way where all the best practices are automatically built in. And so within Square, now known as Block, they were able to turn their most expensive piece of infrastructure, which was their feature platform, and turn it into a highly efficient service where features become data services and they're simply consumable and they're much less expensive because of all of the optimizations that we're doing for their infrastructure under the hood. And so here's a quick example around Tide. This is a financial services company based out of, I believe, the UK. And Tide was trying to go through the approach of, hey, we need to streamline our data engineering and we need to build a feature store, feature platform internally. And they started going down the approach of trying to build it in-house and they started hitting bottlenecks. And ultimately they decided to switch over to Tecton to be the underlying data platform that they need for their features. And you see some of the stats that they've quoted here, double the time to production to be a lot faster, more features are in production. They're able to repurpose 3, FTEs because they adopted Tecton. But most importantly, I think what's interesting on the quote on the far left-hand side is they referred to the value add of features as IP. Like features are IP. That's your data. Those are the signals that are going to allow you to build the best predictive models that is possible. But what they don't see as IP is the compute orchestration layer that's under the hood. So how do we optimize that or really automate that aspect, hand that off to Tecton so that they can focus on the value add aspect on the top simply by interacting with their features? And I think what Hendrik Brackman had said from Tide is really resonant of what our customers see as the ultimate value of partnering with Tecton as their feature platform for production ML. And so within that, just want to share a quick logo slide. These are a handful of our customers that are currently using our platform and seeing that kind of value across their production environments and their production use cases. And so within that, I just want to close out with one final slide that, again, we really, really appreciate you guys staying with us for the hour and learning a little bit more about how to productionize faster, lower that tech debt, streamline the data engineering workflow that's involved in ML. And if any of this conversation has inspired you, we'd love to invite you over to tecton.ai/explore, where you could actually go through a tutorial and a walkthrough of your notebook in a Google Colab notebook, and you could actually interact with Tecton and see what the declarative framework is like, see what the management and user experience is like, simply at the comfort of your own computer without having to talk to a salesperson, just really on your own and in your comfort environment. So we'd love to invite you over to check out this interactive demo at tecton.ai/explore. And so within that, love to see if we have a minute or two, we can maybe take some of the questions that have been sent over. Sergio.
I've been answering most of the questions. There's, I believe, one that I did not answer, which I'm going back to.
Hey, Sergio, since just because we only have a minute left, is there a particular question that was provided that you thought was interesting, and we could share that publicly with the group here?
There were quite a few questions around streaming. I did answer, and I provided the connections to the docs in multiple cases. You know, how to select a Databricks cluster by specifying Databricks config. So that's there in the chat. The one that I didn't answer was regarding caching. So how we do caching and how that affects serving. So in the feature service, there is a caching function that allows you to define, the caching time frame for features, and can accelerate the serving of features significantly for higher throughputs. But it comes with a cost, right? And that's the time to live that you give those that cache, which means that you're going to you're potentially losing some data freshness there. So it's a choice to make, right? Whether you're going to use caching and for how long, based on your throughput needs and based on your data freshness needs.
Fantastic. I think we are at the top of the hour. So Sergio, appreciate the partnership on this talk today, and for everybody here in the room, thank you so much for joining with us, and hopefully you got something out of it, and excited to hopefully talk with you more. Thanks all.